Welcome to my presentation. Uh, Today my chemistry concept video topic is galvanic corrosion, and myself I am T Naganishit and I am from ECB section, and my roll number is 2195A04C5. First of all, what is galvanic corrosion? Galvanic corrosion, also called bimetallic corrosion or dissimilar metal corrosion, is an electrochemical process in which one metal corrodes preferentially when it is in electrical contact with another in the presence of an electrolyte. A similar galvanic reaction is exploited in primary cells to generate a useful electrical voltage to power portable devices. Corrosion of an iron nail wrapped in bright copper wire, showing cathode protection of copper. A ferroxyl indicator solution shows colored chemical indications of two types of ions diffusing through a moist agar medium. Here in the figure we can see how the galvanic corrosion are happening in the iron nail wrapped in bright copper wire. Dissimilar metals and alloys have different electrolyte potentials, and when two or more come into contact in an electrolyte, one metal that's more reactive acts as anode and the other that's less reactive as cathode. The electropotential difference between the reactions and the two electrodes is the driving force of an accelerated attack on the anode metal, which dissolves into the electrolyte. This leads to the metal at the anode corroding more quickly than in otherwise would and corrosion, and the cathode being inhibited. The presence of an electrolyte and an electrical conducting path between the metals is essential for galvanic corrosion to occur. The electrolyte provides a means of ion migration, whereby ions move to prevent charge build up that would otherwise stop the reaction. If the electrolyte contains only metal ions that are not easily reduced, such as Na plus, Na means sodium, Ca means calcium, K means potassium, Mg means magnesium, Zn means zinc. That's how chemical formulas. Okay. The cathode reaction is the reduction of a dissolved H plus, I don't know, to H2 or O2. O2 means I think oxygen, to OH, right? In some cases, this type of reaction is internationally encouraged. For example, low cost household batteries typically contain carbon zinc cells as part of a closed circuit, the electron pathway. The zinc within the cell will corrode preferentially the ion pathway as an essential part of the battery producing electricity. Another example is the cathodic protection. Cathodic protection of buried or submerged structures as well as hot water storage tanks. In this case, sacrificial anodes work as part of a galvanic couple promoting corrosion of the anode while protecting the cathode metal. In other cases, such as mixed metals in piping, for example copper, cast iron and the other cast metals, galvanic corrosion will contribute to accelerated corrosion of parts of the system. Corrosion inhibitors such as sodium nitrates or sodium molybdate can be injected into these systems to reduce the galvanic potential. However, the application of these corrosion inhibitors must be monitored closely. If the application of corrosion inhibitors increase the conductivity of the water within the system, the galvanic corrosion potential can be greatly increased. Acidity or alkalinity pH is also a major consideration with regard to closed loop bimetallic circulating systems. Should the pH and corrosion inhibition thus be incorrect, galvanic corrosion will be accelerated in most HVAC systems. The use of sacrificial anodes and cathodes is not an option, as they would need to be applied within the plumbing of the system and over time. would corrode and release particles that could cause potential mechanical damage to circulating pumps, heat exhausters, etc. Examples of galvanic corrosion. You all should know. A common example of galvanic corrosion occurs in galvanized iron sheet of iron or steel covered with a zinc coating. Even when the protective zinc coating is broken, the underlying steel is not attacked. Instead, the zinc is corroded because it is less noble. Only after it has been consumed can rusting of the base metal occur. By contrast with a conventional tin can, the opposite of a protective effect occurs. Protective effect occurs. Examples of galvanic corrosion. Array, you all should know, no? A common example of galvanic corrosion occurs in a galvanized iron sheet of an iron or steel covered with a zinc coating. Even when the protective zinc coating is broken, the underlying steel is not at. Instead, the zinc is corroded because it's less knowable. Only after it has been consumed can rusting of the base metal occur. By contrast with a conventional tin can, the opposite of a protective effect occurs because the tin is more noble than the underlying steel. When the tin coating is broken, the steel beneath is immediately attacked preventionally. Here we can see the Statue of Liberty. You all know Statue of the Liberty. Statue of the Liberty. Galvanic corrosion in the Statue of Liberty. After construction of Statue of Liberty, we can see the galvanic corrosion there. That's my topic today. Regular maintenance checks discovered that the Statue of Liberty suffered from galvanic corrosion. Here in the upper picture, we can see how the galvanic corrosion works in the Statue of Liberty. A spectacular example of galvanic corrosion occurred in the Statue of Liberty when regular maintenance checks in the 1980s revealed that corrosion had taken place between the outer copper skin and the wrought iron support structure. Although the problem had been anticipated when the structure was built by Gustav Eiffel or Frederick Battle Division in the 1880s, the insulation layer of shellac between the two metals had failed over time and resulted in rushing of the iron supports. An extensive renovation was carried out with the replacement of the original insulation with PTFE. The structure was far from unsafe, owing to the large number of unaffected connections, but it was regarded as a precautionary measure to preserve a national symbol of the United States. Preventing galvanic corrosion, aluminum anodes mounted on a steel jacketed structure. Jacket. Electrical panel for a cathode protection. Here we can see the electrical panel for a cathode protection. These all should made up of the galvanic correction. That's easy topics. Electrically insulate the two metals from each other. If they are not in electrical contact, no galvanic coupling will occur. This can be achieved by using non-conductive materials between metals of different electropotential. Piping can be isolated with a spool of pipe made of plastic materials or made of metal material internally coated or lined. It is important that the spool be a sufficient length to be effective. For reasons of safety, this should not be attempted where an electrical earthing system uses the pipework for its ground or has equipotential bonding. Metal boats connected to a shoreline electrical power feed will normally have to have the hull connected to earth for safety reasons. However, the end of the earth connection is likely to be a copper rod buried within the marina, resulting in steel copper battery of about 0.5 volts. Additionally, the hull of each boat is connected to the hull of all other boats, resulting in further batteries between propellers, which may be made of bronze and steel hulls, which may cause corrosion of the expensive propellers. For such cases, the use of a galvanic insulator is essential. Typically, two semiconductor diodes in series in parallel with two diodes conducting in the opposite direction. This device is inserted in the protective earth connection between the hull and the shoreline protective. Ensure there is no contact with an electrolyte. This can be done by using water repelling compounds such as greases, or by coating the metals with an impermeable protective layer such as suitable paint, varnish, or plastic. If it is not possible to coat both, the coating should be applied to the more noble the material with higher potential. This is advisable because it is coating is applied only on the more active material. In case of damage to the coating, there will be a large cathode area and a very small anode area, and for the exposed anodic area the correction rate will be correspondingly high. Here we can see the galvanic series. Galvanized mild steel cable ladder with cohesion around stainless steel bolts. Here we can in the figure we can see the steel bolts having a galvanic cohesion. All metals can be classified into a galvanic series representing the electrical potential they develop in a given electrolyte against a standard reference electrode. The relative position of two metals on such a series gives a good indication of which metal is more likely to corrode more quickly. However, other factors such as water aeration and flow rate can influence the rate of the process markedly. And thank you.